Okay, I'm going to try something different here. So this is for William, or Will. So we're looking at question 2 here, and it says a ball is thrown straight up, when the ball reaches the highest point. What's the answer? And so here I've drawn it out that the ball starts down, gets thrown up, and comes down. So we know that as it goes up, its velocity is positive, going in the upwards direction, then gets smaller and smaller and smaller, gets to 0 at the top, and then becomes negative as it falls back down. So its velocity is not constant. The velocity changes the whole time. The acceleration is gravity. That's always going to be down. So the acceleration is always down. So out of your answer choices here, if we look at acceleration first, we have acceleration is 0, acceleration is not 0. Those are your two answers. Well, it's definitely not 0. It's always gravity. So we know that it's going to be not 0. And so that's actually this choice and this one. So now we're looking at its velocity, but we have to look at just the highest point. Well, at the highest point, your velocity in the y direction is 0. So if it's thrown straight up, we only have y. So velocity has to be 0 at the top, but the acceleration cannot be 0. So hopefully that makes sense. So let's go to the next one here that you missed. So looking at number 4, and it says in a circus parade, a clown is standing and on a float, moving at a constant forward speed, drops a fake dumbbell. So here we've got a float, we've got a clown standing on it, and he drops his fake dumbbell. So if he was just standing there, it would just fall straight down, right? But since the float is moving, he's going to drop it, and eventually, the float will be over here. But the barbell will hit the ground here, so it's going to go along this parabolic trajectory, if you will. It says, who would observe the dumbbell falling straight down? Well, for the clown, from his perspective, if you look like a top-down perspective here, it's like this is the clown on the float. He's going to drop the dumbbell, and it's going to stay right with him the whole time. So when he lets go of it, it's going to hit the ground, but it's going to hit the ground right next to him, just like this. As the cart moves along, so does the dumbbell, so does the clown. So only the clown is going to observe it moving straight down. The child would see it move in this parabolic arc, but the clown would see it move straight down. Let's see here. The next one, it says the projective vector along a coordinate axis of a coordinate system. So here, this is number 5. Let's label this. Number 5 says projection of a vector. So we have a vector. So we take our coordinate system here. We've got y and x. That's not y. Y and x. And so we've got this vector here. And so remember we talked about we can break a vector into its components. We have an x component and we have the y component. So in either case, the projection is called the component. So this is a component, that's a component. So that's what it's saying. When it says projection, you can think of like this pencil right here. So it's going up at this angle. If I was to shine a light down on it, it would have a projection in the x direction, or if I shine a light from this side, it could have a projection this way. So you have an x projection this way and a y projection this way. So that projection, instead of calling it a projection, we say it's the component. So that's just the definition of component. Got those? That's good. Let's see here. Okay. So machine, number 10. We have a machine launches a tennis ball with an angle of 45 degrees. And it gives us all of these things. It says we have an angle theta of 45. We have a v horizontal, so I'll call it Vx, of 9 meters per second. We have a Vy of, again, 9 meters per second, which makes sense because it's at 45 degrees. And it gives us the time, 0.92 seconds. But we have to be careful here because it says it launches it and it lands. And the time is going to actually be from where we start here to the max height. So the time, this time is only for this first section, from here to there. Okay. Then it wants you to find the total horizontal distance. Well, it wants you to find this, right? I want you to find this total horizontal distance. Well, we know that for x velocity, so we don't have to worry about y, velocity is displacement over time, right? So to find displacement, we're going to multiply both sides by t, so I'll cancel. So delta x would equal velocity times time. Okay, so the attempt here is to just do 9 times 0.92, but remember that's only the time for half. So we need to multiply this by 2 to get the whole time. So I'll do delta x equals v, which is 9. That's not going to change. But now for my time, I don't want 0.92. I want 0.92 times 2. So I can do that. I can do 0.92 times 2. So I multiply this times 2, and I get 1.84. And so that is the time of the whole thing, 1.84 seconds. So delta x should equal that times 9, 16.56 meters. All right? Okay. So that should be our answer. So here, yeah, the closest is just going to be 17. The resultant of two vectors is smallest when the angle between them is this, and the largest when the angle is that. So here you got two vectors. So imagine you walk as vector 1, and then you have a second vector here. So the angle is this angle that we're talking about right here, because you're walking and then you turn. So like this angle will be like 60 degrees or something. So it's asking, okay, when can you get this resultant? So remember, your resultant is from where you start to where you end r. And it's asking when can it be the smallest and when it's the biggest. So here, if you're looking at this, you can see that if I make this arrow go further this way, like it comes over here, this resultant would be larger. So when do we get the largest resultant? Well, we get our largest resultant when we do this one plus another one going straight. So this angle right here that the second one makes with the x-axis is 0 degrees. So you get your largest angle when this is 0. Then if you want to get your smallest, well, you got this one going, and then your smallest is actually going to be when you go backwards like this. And so the angle between this guy and the x-axis is going to be 180. So largest angle when they're at 0, smallest when they're at 180. Looks like you got that one backwards. So this one here looks like we had a bad unit conversion, I think. So number 12, they want you to find how far you travel. So it's just like this one here, that x is velocity times time. And it gives you the velocity as 15 kilometers per hour, but it gives you the time as 3 seconds. So you can't just multiply these because these aren't the same unit, and then in addition to that, it wants the answer in meters. So the first thing we need to do is convert this, say, from seconds to hours. So I know that x equals 15 per hour time, so let's convert this. So we have in 1 hour, there are 3,600 seconds. So I'm going to, if I want this to be in hours on bottom, sorry, I want to get rid of the seconds, so seconds should be on bottom, hours should be on top. So in 1 hour there's 3,600 seconds. So I'll take 3 times, well, 1, and then divide it by 3,600. So I get the answer of 0.00083 hours. So I can multiply that times 15, and that gives me a delta x of 0.0125 kilometers. So now we need to change that to meters, and so we know that there should be 1,000 in 1 kilometer. There are 1,000 meters. So delta x should equal this times 1,000. Now we'll get 12.5 meters. Okay. Let's look at the next one. So got that one good, good, good. Oh, well. Okay, so this one, number 16. In the graph shown below, what are the displacement from 0 to 6 if the initial position is 0? So initial position 0, so that makes things easy. So if you're looking at this graph here, so we can sketch that out, and we've got here to here and over there. So we don't have to worry too much because we're only going from 0 to 6, so it's from here to there. So this is a velocity time graph. So remember that the acceleration on this graph is slope, and displacement, we'll say delta x, if you will, is the area under the curve. So here it's asking us to find the displacement, so we're looking for this. So if we're going from 0 to 6, let's see here, this is what, 2, 4, and 6, obviously my sketch is not very good, but we know that this thing goes up to 20 here. So we're just going to find these three areas. So we've got one triangle here, one triangle here, and then a rectangle. So this one has a base of 2, a height of 20. This has a base of 2, height of 20. And this has a base of 2 again, and a height of 20 again. So remember, this one is going to be just length times width. So 20 times 2 is going to be 40. And then this is going to be 1/2 length times width, and 1/2 length times width. So this will be 20 times 2 times 1/2. 1/2 times 20 times 2. So 40, half of 40 would be 20, so you get 20 here, 20 there. So for the whole displacement from 0 to 6, we get 20 plus 40 plus 20. So all three of these added together give us 80 meters. All right. Got 17, good. 18, good. 19, good. 20, good. So 21. Baseball is thrown from here to there, reaches maximum height. Find the, it does say find, the angle of launch of the ball. Okay, so this is a good, it'll take us a second here. So if we draw it, it's launched from first to second base, which tells you that it's going to land and be launched at the same height. Oh, let me get out the camera. We know this is halfway, right? So it gives you the maximum height, which would occur halfway in this case, 6.42 meters. And then it gives us the range as 27.43 meters. And it wants us to find the angle of launch. So this is going to be launched at some angle, theta. Okay, so this one is going to take us a few steps. Because in order to find the angle, we have to find information about the sides of the triangle. So, because we don't know anything about the triangle other than, let me zoom in on the triangle here. So if we just think about the launch velocity here, this is the triangle we're looking at. So we got Vx and Vy. So we're trying to find this angle. Only thing we know right now is this is 90 degrees. And we know this is the hypotenuse, we know this is the opposite side, we know this is the adjacent side. So we're going to need, since we don't know any of the other angles or any of the sides, we need at least two more pieces of information. So probably the easiest ones to get is going to be, well, your Vx and your Vy. So let's get those. So here it gives us the height. So we can think, what if we just cut this parabola in half? Just cut right here. If we cut right here, we know that the velocity in the y direction is 0. And it's going to go from here, and it's going to fall down. Okay? So what we can do is we can say, okay, if I put my origin, let's say on the ground here, so this is 0 height, this thing, at this point, its y height would be 6.42 meters. Okay, so if we want to find that, we know y, we can say this is y naught if it starts here and falls down. This will be your final y. And so if we're looking for time and we have these things, we can use our second kinematics equation. So y equals y naught plus v naught yt plus 1/2 AYT squared. So y, we said was 0 because it's going to land on the ground. So again, we're just cutting this in half. Y naught would be 6.42 meters above the ground, plus Vy, and so this is why we did this, because we know this is 0 at this point, because we don't know of any of the velocities. So we're going to do plus 1/2 -10 t squared. So that gives us 0 equals 6.42 minus 5t squared. So we can add 5t squared to both sides. I'll cancel, so we get 5t squared equals 6.42 meters. We can divide both sides by 5. So we get t squared equals, what's the 6 point? Oh, put this on. 6.42 divided by 5. Maybe 1.284, and then we can take a square root of that. And t equals, whatever that is. 1.13. So that's going to be the time for half. So the time for the whole thing, we'd have to multiply by 2. So this times 2 is the time of the whole thing. 2.26 seconds. So to find your x velocity, well, we just do distance divided by time. So Vx is distance divided by time. So distance is 27.43. And the time is 2.26. So 27.43 divided by 2.26. So we get an x velocity of 12.14. So now we need a y velocity. Well, we can easily find that from Vy equals V naught y plus AT. And again, if we just consider half, then we can use half the time. And we'll solve for Vy. We know it's 0 at the top, minus 10 times 1.13. So Vy would equal -10 times 1.13. So negative 11.3. So that's what it's going to be falling down. So we know it's negative here, but positive over here. So your initial velocity, V naught y, would be just a positive 11.3. So how does this get us our angle? Okay. Well, we've got these two, and we're solving for angle. So it's just like tangent inverse of opposite over adjacent. So the opposite would be Vy, so 11.3 over 12.14, and theta is whatever that is. So 11.3 over 12.14, we get 42.9 degrees.
Alright, and that's all I have time for right now.